This video is in chapter 3. It is meant to give you much more detailed help on how to create piecewise graphs. This is the first of 2 videos you will be watching tonight. It would be very helpful if you had some colored pencils, or maybe like a pencil and a blue pen, or a colored gel pen or something like that, and also some graph paper. So if you need to pause this video to go collect those things, I recommend you do so. It will make your notes a lot more helpful. All right, the idea of a piecewise function is where you have 2 or more functions put together on the same graph. And depending where you are on your x-axis or where you are in your graph, you will use information from different functions. So it's like a bunch of functions put together, or I should say a part of 2 or more functions put together to make one continuous function. So this example, f of x equals x plus 2 and f of x equals x, has a dividing line at x equals 0. If this looks confusing to you, you could think of it as simply y equals x plus 2 when x is less than 0, and think of it as y equals x when x is greater than or equal to 0. So those are the 2 functions we are going to graph, and then we're going to worry about the boundaries for when you look at each function later. So I'm going to start with my first one, y equals x plus 2. I'm going to ignore the domain right here of x is less than 0. I'm going to ignore that for a minute. It should be pretty easy to graph y equals x plus 2. That's a y-intercept up at positive 2. If I were you at home, I'd be using a pencil at this point. And then with a slope of 1, we go up 1 to the right 1 as long as the graph allows, and also go down to the left for as long as the graph allows. Okay? Then my other one, y equals x, well that's like y equals 1x plus 0. So that's a y-intercept of 0 with a slope of 1. Looks like these guys are parallel. I'm keeping these as points right now because I have got to start thinking about the boundary. It looks like I have a boundary line when x is less than 0 or greater than or equal to 0. Well, x equals 0 is a vertical line on the y-axis because that's when x equals 0. That red line there is not a part of my function. It's not a part of my graph. It's more like it's actually imaginary. So don't worry, won't actually be there in our final answer. But what it's saying is this graph in blue, the y equals x plus 2 right here, we only care about that. Whoops, sorry. There we go. We only care about that when x is less than 0. So I look over at this dividing line and I see x is less than 0 here. So I want this line here, and then I don't want any of it when it's greater than 0. So I'm going to get rid of those guys. I think I accidentally got rid. Add that guy back in, that guy back in. All right. And then my guy in green, y equals x, I only want that when x is greater than or equal to 0. So here's x equals 0. When x is greater than it, I want it to the right. So I will get rid of what's to the left. Then there's this issue of less than 0 or greater than or equal to 0. The y equals x plus 2 is when x is less than 0, so it actually doesn't want this point here. So I'm going to put an open circle with my blue function. And then you want when the y equals x, it's when x is greater than or equal to 0. So for my guy in green, I do want it included at x equals 0. It's important along this dividing line to remain a function. Remember, you can't have 2 y's for more than 1 x. So it's really, you can't have more than 1 y for every x. I said that funny. So here, we've got this x value. When x is 0, y is 0. So that means we can't have this one. So it's important that this top one is not colored in because it's not included. So you have this continuous function. It follows the blue. And then as soon as it gets to this dividing line, it does not hit x equals 0. It jumps down and picks up on the green as it continues going. So officially, if I was going to graph this piecewise, I would take the dividing line out. You can certainly keep it on. I'm not going to be that picky. And then if you wanted to make that a little better, so it's very clearly an open circle right there, you could. That is what the piecewise function looks like. It's a part of each function to make one continuous one. Let's try another. This one's a little bit more complicated because there's three functions on my graph. I've got a y equals absolute value of x, a y equals 2x plus 1, and a y equals quantity of x minus 5 squared. I have dividing lines at 1, 4, and 7. I might, like maybe lightly with a pencil, remember this is the x equals 1 dividing line, and then I have one at x equals 4. These are imaginary, they're not actually a part of our function, it's just helping us get organized as we make it. So it's kind of like I need, it looks like y equals the absolute value of x when x is less than 1. So everything over here is going to be that function in blue. And then my next function, y equals 2x plus 1, happens when x is between 1 and 4. So that function we're going to show in that space. And then we've got the quantity of x minus 5 squared. Well, that's going to happen when x is between 4 and 7. So we're going to have one continuous graph from the left all the way up to x equals 7, but it's going to be from different parts of a function. I think it's really important to remember the origin is here. When we graph things, we still have to remember where the origin is. Here's our x-axis. Here's our y-axis. I did the graph paper a little bit different, just so we get in that better range. So here, y equals the absolute value of x. Well, I know the absolute value, v, there's no, that's just the parent graph. So at the origin, and then this is going to be when x is less than 1. So I could go this way as long as the graph allows. I could go this way as far as the graph allows too, but I know I'm going to stop because I'm getting better and seeing, oh, it's only when x is less than 1. So I'm going to put an open dot here at 1 and color in the rest. Put an arrow because it'll go forever to the left. That's why I like having those boundary lines in, so sometimes you don't have to draw more and erase later. If you've got those boundary lines in, you know when to stop. Okay, so for my second one, I'm going to use green, y equals 2x plus 1. Well, I know that that is a slope of 2, a y-intercept of 1, and this is a little bit trickier because I'm starting, the y-intercept of 1 is not in that range of 1 to 4. So I'm going to lightly use a pencil if I were you. Starting up at 1, and then a slope of 2 is up 2 over 1, up 2 over 1, and then I get to the other boundary. So if I'm between 1 and 4, I really only want these guys right here. So this guy, let's see if I can erase him. He was kind of just helping me. Oh, I'd erase the whole thing. I thought that might happen. We had an open dot there. All right, so looking up here, if x is greater than or equal to 1, on that green function, greater than or equal to would mean I color that in. And then if x is less than 4, that would tell me that up here at the boundary line of 4, when I went up 2 over 1, that would be open. Still have that. All right, and now I have to do my last piece of when x is between 4 and 7, I get this function of y equals x minus 5 squared. Well, that's a parabola that's moved to the right 5. So that's nice. So from the origin, I'll count to the right, 1, 2, 3, 4, 5. And then it has an a value of 1, so it's just going to be that normal stretch of 1, 3, 5. So up 1 over 1, up 1 over 1, that hits the boundary on the left. And then up 3 over 1 hits the boundary on the right. So I make my nice curve. And let's see about colored in and open dots. If x is greater than or equal to 4, on that boundary of x equals 4 will be a closed dot, but it says it's just less than 7. So on that boundary line of 7, I'm going to do a better job of making it look like an open circle. All right, so when I do my vertical line test for a function, let's see, from left to right, I should have for every x, 1y, it's continuous. I'm looking good, looking good, looking good. When I get to this first boundary, it's colored in on the green and open on the blue. So it passes the vertical line test because it's passing at the green. There's nothing there at the blue. Now I keep following the green. Maybe I'll make this a little bit longer if I can. Oh, no. There we go. When it turned a little, that's not right. All right, let me try there. All right, so we're following the green. When we get to the next boundary, it still passes the vertical line test there because that open circle on green, it's not a part of that function. It's hitting the function down here on the red one. So I know I'm doing pretty good. I keep going, I'm following the red, following the red. I get to this boundary, it's an open circle, so that kind of tells me that the function doesn't exist there and it doesn't exist moving on. So it goes all the way, the domain is from negative infinity up to just under 7, because once you get to 7, there's an open dot there. If you wanted to clean up your picture, you certainly wouldn't have to. You can erase these imaginary lines. If you want to keep that there, so when you refer to your notes, you can kind of remember how you did this, that's fine too. I just kind of wanted to give you a chance to see what it actually looks like. That was what the piecewise function would actually look like without all the extras. All right, now this last example is working backwards. In the first two examples, I gave you the equations and you had to graph. In this one, I'm giving you the graph and you have to write the piecewise function. It doesn't say, but let's say this graph, the piecewise, is f of x. So then you know to start, you'll have f of x equals, and then you do those squigglies. Now how many boundary lines are we dealing with? Like how many different sections of graph do we have? I definitely see a boundary line here, and I think it's obvious to see a second boundary line here. So I look at that, and all of a sudden, my piecewise graph, I can see 3 distinct different parts. So I'm going to need room for 3 here, and I think I didn't leave myself very much. Maybe this will help. I'll spread that out a little bit. All right. Now let's set up the boundaries. Okay, so my first one, I'm going to have this function. I'm going to call it the blue one. It's on the left. It looks like it goes, let's just put an arrow here and assume it goes to negative infinity and it stops. This boundary line is x equals negative 2. And I notice that there's a colored in dot there. So whenever x is less than or equal to negative 2, it's going to be this line right here. So that would be my first boundary when x is less than or equal to negative 2. All right? Then in the middle, this guy, this parabola, I'm going to use green as my color. I see an open dot. And then on the right-hand boundary, I see a closed dot. And it looks like it goes from x equals negative 2, and then this other boundary is x equals positive 2. So how I write that is I will do a negative 2 on the left, a positive 2 on the right. And let's see. It's going to be bigger than that negative 2. It's an open dot, so I'm just going to have that sign, but it's less than a positive 2. It's less than or equal to a positive 2. So I have the less than or equal to there. So remember, open dot is just greater than or less than. The closed dot is greater than or equal to, less than or equal to. All right, and then my third function, I'm going to have it be red here. It's just a straight line. There's an open dot at the boundary of x equals 2. So I'm going to say when x is greater than 2, I'm not going to say x is greater than or equal to 2 because it's an open dot. That will be my third function. Well, this third one seems really easy. What is that? It's just a horizontal line that if you continued, it would pass through the y-intercept of 6. So that is, that equation, you could think of it as y equals 6. Some people might think of it as y equals 0x plus 6. But all you would write here is that this f of x, that's like the y part. So if we're going to write f of x equals 6, all you put in here is the 6. Because you've already got the f of x equals. All right, the middle one. Let's take a look at the middle one. We're working in green. It has an origin, a vertex at the origin, up 1 over 1, up 3 over 1. So I've got, I don't have a stretch or a dilation. It's just the A. It didn't translate. So that's just going to be, it's just our parent graph parabola. F of x equals x squared. You only write the x squared part here because you already have the f of x out front. All right, now moving to our last one. This might be the trickiest one because it's kind of far away from the origin. I can see the slope pretty easily as a -1. I go down 1 to the right 1. But where's the y-intercept going to be? Is it -5? No, that's where it intercepts the boundary. We have to keep going till we get to the actual y-intercept of -7. So that equation is y equals -1x minus 7, or you could say f of x equals -x minus 7. And since the f of x is already there, we're just going to write a -x minus 7. So that is the full piecewise equation. So you will be expected to be given a piecewise function to graph it, and you'll also be expected, given a graph, to write the equation down. That is it for this video. Hope it helped.